お待たせいたしました。それでは TE-07 米国における IoT ビッグデータ&アナリティクス活用事例の最前線を開演いたします。講師は Amazon Web Services プリンシパルソリューションズアーキテクトMihaクラーリ、そして同じく Amazon Web Services ビジネスデベロップメントシニアマネージャーのユージーン川本です。それではお願いいたします。
Welcome, and thank you so much to choosing this session this afternoon. I'm really honored that you decided to come and choose this one among all of the sessions that are available to you. So thank you so much. I hope that in next 40 minutes, Eugene and myself will tell you a little bit about how we are actually addressing that completely new domain of problems that we are seeing with those small, loosely connected and highly constrained machines that in the industry we call Internet of Things. So we will divide this talk into two parts. We will talk on one side, first 20 minutes, I want to talk mostly about how do we reach out and approach the devices, those little things, or monos as you call them in Japan. And the second part, after we harvest all of the information, all of the data into a ginormous data lake, how do we actually do some smart analysis on top of it? But before we start with looking into the development programming models and all of the telemetry and everything that we can do on small, loosely connected devices, let's first define what makes those things in the Internet of Things different from traditional computers. So definitely, number one constraint that we see when we talk about Internet of Things is that those devices always have at least one constraint. They can be constrained on the memory or on CPU. Most commonly, they're all constrained. All of the Internet of Things devices are constrained on the networking side. So when you are thinking about how do you program for that, something that has a really tiny little simplified footprint and you cannot reach as often as typical connected, well-connected computing devices. The second big difference is that we are treating things, monos, in extremely high volumes. We are no longer talking about tens or hundreds or thousands nodes. We are now talking about hundreds of thousands of machines, and actually we need to create architectures that can easily scale all the way up to very much absorbing. First, we need to address millions of machines, but also we need to absorb all of the information and telemetry coming from millions and millions of the machines. Now, why is that really relevant is, as you are looking how we are evolving through last, I would say, 30 years, we are going from few large, powerful machines into more and more and more smaller and smaller and smaller machines. So those machines are playing more and more critical role in our lives, and when it comes to Internet of Things, we don't have much of interaction with them. So we need to create completely different models for all of those devices that have no screen, no input, no output for human eyes. So this is the beginning of machine-to-machine era, where we need to create all of the right structures and patterns and approaches that we can actually develop machine-to-machine type of protocols, communications, action, reaction, reprogramming, everything that comes along with it. If you go to Wikipedia, it's actually very interesting how Wikipedia defines Internet of Things. Some parts of the definition absolutely we agree with. There is at least one that I personally don't agree with. The most important part definitely is that when we are talking about Internet of Things, we are talking about network of devices that achieve some value and service in just data exchange. Either we harvest from sensors or we push some information out and we want to generate some additional value out from it. It's interesting that, as you will see the patterns that we evolved in the Internet of Things domain, we are now starting to reuse the same patterns in regular computing world as well. And we can see some organizations that use the same approach and say, well, my servers are nothing more than things running in a cloud. So the moment when you have a company running 50,000 or 100,000 virtualized servers, you treat them as things, and you kind of treat them in almost the same manner as 100,000 of sensors or 100,000 of Raspberry Pi devices. So let me clarify, when we are talking about Internet of Things, what are those small things and what they are not? One of the things is that when we have Internet of Things approach, we are usually talking about devices with no human interaction. So Internet of Things is not necessarily made for something that has screen as an output, and it's not made for something that has a keyboard as an input, because we can do way richer. First, screen can give us much better feedback if we can look at the device and verify is it running fine or not. Most Internet of Things have no display. And the keyboard or any input type of on a sensor would also help us to program it, to reset it, to do anything of that. And that's why small things usually have no ability for human interaction, either as an input or as an output. So phone is not really a thing in a usual definition, while Raspberry Pi would be one. The other big definition, separation is also, can you actually reach out to the device? A typical example would be a pacemaker. Once we put it into a human body, you can't really go in there and fix it if it's broken unless you open a person again. And we want to avoid that. So hard to reach devices are much better target for Internet of Things compared to the devices that you can actually easily repair with a screwdriver and with the whole regular mechanical approach. So think about a sensor on the tip of the oil drill that goes deep down under the crust of the earth. That would be an Internet of Things. On the other hand, the video recorder or DVD player is not really a thing because you can easily reset it, reboot it, and change things there. So with that, here is the core conundrum that we have. We have that plethora of things out there, and more of those devices we have, and smaller they are. And less of direct interaction we can get with them, more and more we depend on the stream of information coming from them. So the smaller the devices, the bigger the data stream from all of those devices coming out from them. Every individual device needs to tell us way more how it's behaving, and we had a way more in a summary number how many of those devices are out there. And that creates a whole bunch of completely new challenges. Let me show you one example. We have one of our solution architects back in Seattle. He is a very, very avid beekeeper. And he really cares for his beehives and his bees. And in case you don't know how, this is a very, very hard profession because beehives need to be just at the right temperature. If it is too hot on the inside, bees actually have extremely hard time either producing honey or actually they start dying. So the whole idea was to try to help a beekeeper instead of trying to guess, is it too hot, is it too cold, should I move the beehive from sun to shade or not. The idea was to actually try to create a good Internet of Things approach. Part of that to learn and part of that to actually make the work of a beekeeper much easier. So the approach was to grab the Raspberry Pi and attach literally two temperature sensors on it and connect it correctly back to the internet and create a back-end solution that I will show you how to do it. But idea was that Raspberry Pi as an Internet of Things, as one thing, is able to regularly catch external temperature, internal temperature, and send it up to the cloud in regular intervals, allowing us to do the proper analysis on it. So if you're looking from the architectural perspective, it's not that complicated, right? You grab a beehive on the left side, and there is a very simple Python script that runs on the Raspberry Pi that is sending the data up to our Kinesis stream, which is able then to actually aggregate the data, push it over to DynamoDB, and that's where we actually then generate the proper dashboard and proper all of the, let me show you how a dashboard looked like. So very much we are collecting two signals. It's external temperature and internal temperature, and we were able to make the proper dashboarding of how these things work. So Raspberry Pi on its own is really very, very constrained device. But with the right architecture, harvesting all of the telemetric data gives a beekeeper a very, very reliable source of information and a feedback loop. Based on the temperature graphs, then the beekeeper can decide what to do further. Just as an example, but if you're looking at a typical sample Internet of Things architecture, when you look into that one small thing and one mono, what do you want to do with it? We are looking very much into the four big challenges in here, and I will very quickly guide you through these four, and then after we actually get all of the data, Eugene will show you what to do with it on the back end. What are the four core challenges? How do we develop a code for the devices? How do we send commands to those little devices? How do we grab information out from them, so the high volume telemetric harvesting? But probably, particularly in this secure world that we live in, how do we do auditing and how do we do the proper authorization so only the right devices get the right commands? We don't want just anybody to command and reprogram, for example, a pacemaker or a car or a fridge or whatever device actually becomes smart enough that can be included into the Internet of Things. So let's start first with sending commands over. So a big issue is that sending the correct command matters. You don't want, when you have hundreds and thousands of intelligent devices out there, delivering the right command to the right device is not trivial, particularly when we are talking about devices that have a minimal possible connectivity out there. So when we are talking about sending a command, you always need to start thinking about the architectures that are highly transactional. You always need to get confirmation back from the device that command was accepted, understood, and executed. So looking into the architectural view, how are we actually driving those commands? How do we tell devices to do something? The transaction, actually, you can see it in a step 2 and 3. So first one is we need to verify the configuration of the device. Is this the right device to get the command? But much more relevant it is to push the command out from the limited set of possible commands for this device and then get the success or failure, but definitely get the feedback back into our system from the device itself. On the right side of the picture, you already see that we are starting to look into the architecture who can actually drive a command. So our Cognito for authorization is already one of the very key services, and also you see DynamoDB on the left side to either get configuration, to read commands, to push commands, and actually to store all of the confirmations back in. Now, when we are talking about the core challenges in development, this is even bigger problem than sending commands, because if you send the wrong firmware out to the device and you kill it, it is dead. And if we're talking about devices that are in such a constraint that you cannot physically change or reboot or do anything, you can only very much forget about them. So if you kill with wrong programming a device in the production, in Internet of Things, you don't have much of a help left. And that's why it is extremely important that the development pipeline has all the right exception management, has all of the right proper stages, that we validate correctly that the code rolls from one stage to another, and the updates which we decide to apply to those devices actually are correctly validated and tested. So a typical architecture to send the firmware update or the whole package. So we want to update a vessel, we want to update the code that runs on that vessel within a small thing, within that sensor thing. We want to actually verify, is the device right? Is it at the right version? Is it at the right state? Grab the bundle. So every device set needs to get its own bundling and then move over towards executing it. A more complex thing, whenever you are in a DevOps practice, you do all of that in a staging environment. So in staging, usually you create devices that actually you can reboot, you can fix, you can check. And that whole idea of having a farm of staging devices is becoming more and more prevalent before you push it over to the production system. The next one is auditing and authorization, where very much the challenge is that we need to understand that there is a very limited set of other machines or users that are allowed to do things, either get information or push information. So architecturally, in cloud architectural world, we again use Cognito for Cognito ID to identify that this is the right device, that this is the right user, and there is the right set of commands that we allow to execute over there. So these are the first three problems. The fourth one, which is probably the hardest one, is telemetric challenge. So we have now hundreds and thousands of those devices that we want to harvest all of that information happening there on all of the sensors and bring them back together. So we have sensors, they grab information, and we start pushing it to persistent streams over to our kind of a tricklets or kind of a small stream harvesting. And we can do then analysis, we can do all the correlation on the data. At minimum, we want to archive all of that and actually have it there for a later consumption. That would be a small amount, a small trickle. Then when you go to a much higher volume of data, you need to start looking much more industrial stage, where we are talking about the machine-to-machine brokers, turning into those streams into a really large streams, and at the end, actually, we flow them into rivers. So you can start combining. Think about it. Trickles go to streams. Streams go to ginormous rivers of data. And with that, you suddenly, on the other side, you get that humongous data lake with all of that time-bound information, all telemetric data coming from an airplane engine, coming from a turbine, coming from whatever is that thing that you are actually harvesting telemetric data from. Just to recap, right? My part of the session mostly focused on how do we actually deal with the sensors itself, with the small things. Eugene will tell you much more about what do we do on the back end. But looking from perspective of what web services, we have a huge amount of really well-tuned web services in Amazon Web Services portfolio, from DynamoDB and Kinesis to actually do that high-velocity data capturing, Cognito to do the proper authentication, all the way to the other side, simple queuing service, simple storage service, and all the ability to auto-scale and do the elastic kind of a breathing in and out, depending how many sensors per time unit are actually coming to your systems. And with that, I will invite Eugene to the stage to show you how we deal with the data on the back-end side.
Thank you, Miha.
Thank you so much.
ありがとうございます。皆さんこんにちは。
Good afternoon, everyone. My name is Kawamoto from AWS. It's been 4 years since I joined AWS. I was in charge of the business development in Japan, and 1 year ago, I was moved to Seattle to develop the business. Well, right now, I am in charge of the database as well as analytics. I am in charge of the global business development. So Miha talked about the IoT, or rather, he was talking about front end. I am going to talk about the back end. After we collect the data, how can we leverage those data and what do we do with those data is something which I am going to focus in my presentation. Well, big data, what is big data? And I think people may ask. So I try to simplify big data, decompose different components so that you will get the better understanding about big data. So maybe you can consider this as one framework. This is not the sole solution, but let me get into their presentation. Well, when we say big data, there are a wide variety of different tools. Yes, AWS also offers different tools. In this morning, in keynote address, DynamoDB, it's a scalable database, and also the relational database engine is managed as RDS. And also, as you may know, S3 object storage, Redshift, which is a data warehouse. So it's really hard for you to choose which one. And also not just AWS, but there are a wide variety of tools as open source or commercial. Hadoop type of ecosystem is already a wide variety of different tools, and also every half a year you see new tool, maybe Hive or Pig. Those are the conventional tools, but right now Spark or Impala and Crest. So those are the different tools which can be combined with the traditional tools, and also as a visualization tool, Tableau is one, or Click. So that's another tools for visualization, and also SAS or R are used for the analytics purpose.
So if we further simplify the process, the basic idea is the following. At the end of the day, there are some kind of a data input coming in, and you want to get the solution out of it. So it's basically a pipeline. And why don't we look this into a little detail? I think we can categorize in certain parts. One is the harvesting. How can we collect data? Once you're collected the data, then you have to process the data. Once it gets processed, then you have to analyze the data and you get the answer. For each phase, collection, processing, and analysis, you do need to store the data accordingly at each phase. So we categorized into 4 areas, and I would like to give deep diving on each. First is data collection and storage. Next is event processing. I think in the morning, even today, there are a couple of keynote speakers and also the session speakers talked about RAM and other options. Real-time event processing of collected data. And also the conventional data processing and data analysis. I would like to cover on those points. As for the data collection and storage, we do have such tools available. One big trend we see among many customers is that most of the data first gets collected on S3. We started calling it a data lake. So the S3 is regarded as data lake these days. The different types of data put onto S3, and then we use EMR or Dynamo, Kinesis, machine learning. All these can be combined together. In case of S3, as you know, it's an 11.9 availability. It's like once in tens of hundreds of years, thousands of years, the data may be lost. So meaning that the reliability is extremely high. Durability is high. As for the data collection and storage, we're going to put everything on S3 first. And then, dependent on the data you want, the location might be different. For example, as for the transactional data, it goes to RDS. Most recently, we announced Aurora, which will be launched very soon. We have Aurora tool available. It's a relational database for transactional data. And if it's a file data, then you can go to DynamoDB or S3. The data can be stored either on the two. And Kinesis is available, especially for streaming data. We can put the queue, and it can be brought to backend data. And then you can analyze the data. Backend process and analyze the data. This is just an example of the architecture. It's not IoT, but there are lots of tweets coming in to Kinesis, and then via KCL apps, it goes to Redshift and S3. How much does this cost? For each services, the pricing model is different for each service. This is East Coast in the United States. We use the region in East Coast in the United States. If it's a 3 per gig on monthly basis, 3 cents. If it's Redshift, 0.25 cents per hour. So we have different pricing model for each. And let's say if there are 100 million tweets per day that you've collected data, and if you want to analyze this volume of data, then since it's 100 million, that means it's 5,800 tweets per sec. And for each tweet, the size is about 2K. That means 12 meg per sec. Kinesis shot per hour, it's 1.15 cent. And put 28 cent. And then 2.8 cent. And as Kinesis cost, 76 cents. Redshift S3 cost total $2.8 per hour. In yen basis, that would be about 360 yen per hour based upon this mechanism. So if you're handling 500 million tweets, all collected onto Kinesis and then stored on S3, Redshift, this is the cost that you only pay. So it's very simple to start. You can simply test it out as well. Next is about event processing. I'm sure you know quite well about this. It's about Lambda or KCL apps. We would be using Lambda or KCL apps. Real-time event processing. That's an event-driven programming. Real-time input becomes a trigger that leads to the next action. Let me share some of the use case scenarios. For example, if you detect some errors from the device, data collected in Kinesis, you execute it using Lambda, and then if there's an error regarding the device, then you can push using SMS to take action. Or based upon the behavioral history, you can identify some problems. For example, you are using credit card, and then you find some anomalies there, then you can take action from Kinesis. Or you can monitor performance SLA. Or if it goes underneath the threshold, then you can alert the inventory. And these can be done based upon events. So from Lambda, we can use S3, Kinesis, and DynamoDB Stream as the triggers. So we can combine those three services, and Lambda can send out the event-driven processing. And as for the streaming, I don't know how well you know, but as we announced last year at re-event, we'll be ready to release this very soon. Update history can be picked up by DynamoDB, and backup application can capture the DynamoDB update information. Next is about data processing, the analysis part. We have EMR. This is Hadoop Managed Service. Redshift, the data warehouse is available. Most recently, we've made an announcement about machine learning services as well. Data processing and analysis. This is to give an answer against the questions regarding the data. I'm sure you know about this. It's the world of SQL, or it's the world of data warehouse as we do the analysis. It's about the classification. It's a sentiment analysis in the field of classification. By using Hadoop, you can process using MapReduce. Or as for the forecast, you can forecast the page. You can use the machine learning as well. As for the data processing frameworks, there are two types mainly. One is batch processing. In case of Japan, we have a very long history of batch processing, so you know well. For example, if you use MapReduce for processing, you can make use of batch processing. And the other option is stream processing. For example, on real-time basis, you can have some ad hoc analysis. Then H-base cluster can be used for analysis purpose. Let's talk about IoT and big data use case. One example here, even though it's most advanced example in US, this is an example of Sushiro. Why Sushiro? Because everyone loves Sushiro. And the most advanced example of IoT example is Sushiro. And whenever I talk with the US customers, I always give Sushiro example the first, and everybody loves this story. As you know, Sushiro is a very famous sushi restaurant chain throughout Japan. There are 300 stores. And every time I talk with them, they have more stores. So it's between 300 to 400 stores throughout Japan. So back of the dish, there is a sensor. At each store, there are a variety of sushi-related data Sushiro can capture. What time, what kind of dish was popular, what was leftovers. You can also capture weather information as well. There are a variety of information that gets collected using Kinesis. Why Kinesis for data collection? It's because if you load the data in batch, then the data can grow so significantly, and it's so hard to send out, and it's really hard to retry if it fails. So what they want is real-time processing using Kinesis.
Regarding the architecture, this is a simplified architecture but from Kinesis to use Kinesis application library and then going to store all the data in their Redshift. And also as a visualization tool, we use Tableau, and through Tableau, we do the data analytics. Next is connected device use case. This is DropCam. How many of you know DropCam? Several of you. This is the camera which can be connected through Wi-Fi. This is a surveillance camera and widely adopted in the US. So you install this at homes, and maybe you can actually monitor your kids or maybe your pets. Or maybe if the thief is intruding into your homes, you can actually monitor those intrusion using this camera. Well, they actually migrated to AWS at the end of 2011. The reason is because the volume of the data was exploding. Per one user, 100 gig per month worth of data is stored. I think according to their blog, so they store more data than YouTube. So after migrating to the AWS, they actually exploded the data volume at the scale of a petabyte. And then, of course, they store the data in S3. And then in terms of the metadata tagging, they use DynamoDB. Trying to address the data increase. This is their configuration. So this is quite a simple. It's EC2, S3, DynamoDB, CloudFront, and also EMR to do the analytics. So it's quite a typical configuration. And of course, DynamoDB is the key component in this configuration. As I mentioned in my keynote address, well, at CookPad, the tagging for the video metadata, they use DynamoDB. This is sort of the same use case. So as a tagging for the video metadata, they use DynamoDB. Last use case is weather bug by Earth Networks. And once again, I touch upon this use case in my keynote address. So they actually install all the sensors throughout the US, and they collect the sensor information, trying to predict the hurricane or thunderstorm. They try to predict the location of those storms or thunderstorm. As a back end, they use DynamoDB as its database. DynamoDB3 is used, and from the devices, they actually store the information or data in DynamoDB and then going through Lambda to Redshift or SNS or machine learning. They do the analytics or trend analytics, and also they are trying to identify the devices, and also they can predict the anomaly through machine learning. So that's all for my part. Well, in the future, IoT and big data, we also try to offer different types of the solution for those areas as a business development team, and also including the Japanese solution architect. We always want to help you. If you have any challenges or if you want to try out anything new, please contact us. Also in October, we have an event, reInvent in the US. So I hope that you also can come and attend at this reInvent in Las Vegas. Thank you very much for your participation.
どうもありがとうございました。